So here is the difference between the real address mode and protected virtual address mode. So in real address mode can only address up to 1 MB of system memory and act as fast as 8086 microprocessor, but in protected virtual address mode only 16 MB of it can address maximum 16 MB of system memory. So less memory has been accessed by real address mode. So in real address mode doesn't support the concept of virtual memory, but protected virtual addressing mode, it supports the virtual memory. In real address mode provides no support for memory protection or multitasking or code privilege levels, but in virtual address mode it supports the memory protection, multitasking, as well as the code privilege levels. And in real address mode, initially every processor is in real mode, that is MSW machine status word P bit is set to 0. And if protected mode is to be enabled, virtual address mode, that protection enable flag bit must be set to 1. So microprocessor will switch to this mode by setting the machine status word P bit as 1. So these are the differences between these two modes of 80286 microprocessor, real address mode and protected virtual address mode. Now coming to the descriptor, why this descriptor is so important in protected protected virtual address mode. The smaller segments of pages have been associated with data structure called a descriptor. So actually, what is descriptor? Now descriptor is a block of contiguous memory locations containing information of a segment. Okay, it's a continuous memory location, and all the information of segment is stored inside descriptor. Like segment base address, the base address means the initial location of that segment. What is the limit of that segment? What is the type of that segment? Is it a code segment or data segment or stack segment or anything else? So segment type must be stored. Privilege level is there, because in 80286 there are 4 privilege levels are considered. So which privilege level has been considered, that information is to be stored inside this descriptor, along with segment availability in physical memory, descriptor type, and segment used by whether this segment used by another task. So everything, that means the base address, the starting and location of a segment is very important descriptor information. The segment limit indicates the maximum size of the segment. Using the base address of a segment and the segment limit, one can determine the last location of the segment. Similarly, each segment has a type and its privilege level, which indicates the importance of the segment. The privilege level indicates the privilege measure of a segment. A segment with lower privilege level will not be allowed to access another segment having higher privilege, thus offering protection to the segment from the unauthorized access. Moreover, a certain segment may or may not be present in the physical memory at a given time instant. Then this information also stores inside a descriptor. And finally, an important information, that is whether the segment has been accessed by another task in the past, is also stored in the segment descriptor. Now this information helps in deciding whether the segment should be unswapped from the physical memory or not. Okay. A segment which has not been accessed in the recent past may probably be unswapped from the main memory. So here actually what happened, descriptor basically carry all the relevant information regarding a segment and its access rights. Okay, so the segment based address is a and here is a diagram. Here, so how the physical address is calculated. Here is your segment descriptor is available. Now one thing, Okay, before going to discuss the physical address calculation, first descriptor table is here. So all descriptors, it's a block of contiguous memory locations containing information of a segment, every information. So the set of descriptor is known as descriptor table. All the sets of descriptor table are prepared and managed by the operating system. Okay, so descriptor carry all the relevant information regarding, as I have told you, the segment and the access rights. So every segments must be there. Okay, and this descriptor is very important to create the physical address in protected virtual address mode. And how this will be occurred happened in so look into this picture. The segment based address is a 24-bit pointer, 24-bit pointer that addresses the first location in that segment. This 24-bit segment base address, 24-bit segment base address, this one, this 24-bit segment base address is added with 16-bit offset. So here is your 16-bit offset. Okay, so first selector. And what is a selector? The selector basically, it is a content, 16-bit content of a segment register. Okay, which is used to address a descriptor. So it points the descriptor. Where is the descriptor? In your physical memory. Then from this descriptor, here all the informations are available, means relevant information about the segment, what is it and what is the limit, what is the base address. Now from this base address, it is going inside this segment base address block, so that base address must be given to this physical address, and this offset must be given to this physical address adder, so that the combinations of this offset and the base address, one physical address is calculated, and it points to the memory where this segment is situated. Okay, actual segment. So the maximum segment size will be of 64 kilobyte, since the offset is only 16 bits. And here the calculation of, in this position, the descriptors are automatically referred to by the CPU when a segment register is loaded with a selector. Segment register select with a segment register is loaded with a selector. Okay, so automatically it is referred by the CPU. So in this way, the physical address is calculated in protected virtual address mode. Now here is the selector bits, how the selectors are used. So the contents of the segment registers are known as basically selectors. Okay, the contents of the segment registers are known as selectors. That the selector contains three fields. It's a 16-bit format. The 2-bit field, that is D0 and D1, is called as RPL field, RPL. Okay, which is requested privilege level, requested privilege level. So in 80286 there are 4 privilege levels. So first one is the kernel level, second is the OS services, and third is the OS extension, and the fourth one is the application level. So which privilege level has been selected, you can select it using the 2 bits. If 00, then first level, if 01, then the second, then third, then fourth, as per your requirement. Okay, so it describes the desired privilege of the segment. Now D2 bit, here this one indicates the descriptor table type. Okay, descriptor table type, table indicator. So there are two types of descriptor table. One is the global, another is the local. So if this bit is 0, it selects the global descriptor table. If this bit is 1, then it selects local descriptor table. Now and the next bit is the next 13 bits, that is D3 to D15. These 13 bits are called index. And what is the use of this one? This selects the descriptor entry in table. Okay, descriptor entry in table, descriptor table. And right now, so I will discuss these two things. What is the global descriptor table and local descriptor table? What does it mean? So every descriptor, remember, every descriptor required by a task is either in a local descriptor table or in a global descriptor table. Okay, a descriptor table is an array. What is the descriptor table? It's an array of 8 kilobyte descriptors. Only 8 kilobyte descriptors are available. So descriptors, it's a continuous block of memory which is always 8 kilobyte in size. Now the upper 13 bits of the selector field, this points to a particular entry in a descriptor table. This means that there may be 8 kilobyte descriptors in a descriptor table. Now each descriptor is an 8 byte entry in the table, and each descriptor is a 8 byte. Okay, each descriptor is a 8 byte and your descriptor table is 8 kilobyte. So if the descriptor table is 8 kilobyte and each descriptor is your 8 bytes, then how much total memory you require to store this information? Total 64 kilobytes, because 8k into 8. Okay, so 8 kilobyte is your descriptor table and one descriptor is 8 bytes wide. So 8k into 8, that is 64 kilobytes of memories are required. And obviously to point to 8 kilobyte descriptors, a 13-bit addresses is required, because we know that 2 to the power 13 equals to 8 kilobyte. So 13 address lines are required. Now each selector can address a segment of size 64 kilobytes. There can be at most 8k local descriptor per task, or 8 kilobyte local descriptor, or 8 kilobyte global descriptor per task. That is a total of 16 kilobyte. Okay, 8 kilobyte local, 8 kilobyte global. So total is 16 kilobyte. And how this 16 kilobyte will be generated? Using 2 to the power 14 address lines. So 14 address lines are required. That means A0 to A13. And thus the total virtual memory that can be addressed per task is 64 kilobytes into 16k, which is 1 gigabyte. Okay, 1 gigabyte. So exception 13 will be generated if any attempt is made to refer a descriptor outside any of the descriptor table. So exception 13 means it's one type of interrupt. Okay, so one type of interrupt has been generated if any attempt, like outside of the descriptor table, if anything has to be if anything wants to search it. Okay, but if it is not included in that table, it is outside of that table, then your automatically internal interrupt has been generated, which is called exception 13. A global descriptor table contains global descriptors common to all the tasks, and a local descriptor table actually contains the descriptors specific to a particular task. Okay, so that is the difference, and I will repeat this. A global descriptor table, GDT, contains global descriptors common to all the tasks, but local descriptor table contains descriptors specific to a particular task. Okay, specific to a particular task, and that is the difference between the local and global. So all the tasks may have their private local descriptor table, or the global descriptor table may contain all the descriptor types except the interrupt and trap descriptors. Okay, so different descriptors are available, like interrupt descriptor table is there, in trap descriptor table is there, so different descriptor table is there, but these are all contains in the global descriptor table under this portion. Okay, and local descriptor table contains only the segment, task gate and call gate descriptors. Okay, so call function is there for a subroutine, so call task gate and call gate descriptors along with the segment descriptors. Okay, so here the privilege level. Now privilege level, why you need it so? Because it basically in 80286 it supports a 4-level hierarchical privilege levels, privilege mechanism to control the access to descriptors, and hence to the corresponding segments of the task. The control of the access to descriptors results in the prevention of unwanted or undue access to any of the code or data segments or unintentional interference in the high privilege level task. In this case, like 00, which is the kernel level that has the highest privilege level, and level 4 that is application level, here this has the lowest privilege level. Okay, so the privilege level provides protection within a task. The privilege level actually provides the protection within a task. The operating system, interrupt handlers, and other system softwares can be protected from unauthorized access in virtual address space of each task using the privilege mechanism. Now, each task in the system has a separate stack for each of privilege levels. Okay, separate stack for each of privilege levels. The privilege mechanism offers or denies privilege controls the use of instruction and descriptors. Okay, so actually the capabilities of the privilege mechanism are explored by using different privilege instructions are available in 80286, and a different privilege access is there, like task privilege is there, descriptor privilege is there, selector privilege is there. So to protect basically what is I mean, it is used to protect the unauthorized access. Okay, because every task has its level, privilege level to perform it, so it is divided into several parts, so it cannot authorize to access the other task at the same time. Okay, or the when the current task is executed. So I've already discussed about the GDT, LDT. Now how the descriptor, because every descriptor has its own segment descriptor, like code segment descriptor has code segment descriptor, and data segment has data segment descriptor, interrupt has interrupt descriptor. So these type of different descriptors are available. So here I have given example of a data or code segment descriptor. Now code segment descriptor, it's here. Basically it has a segment for code segment, for stack segment, data segment, every descriptors has been there, but only this descriptor has been given as an example. So each descriptor is 8 bytes long. The information stored in these 8 bytes of a descriptor can be used by the operating system to support the implementation of memory management, as well as to protect certain schemes. Okay, for accessing any program, segment, or page, its descriptor is first accessed, and its access rights byte contents are verified with those of the requesting program. Now, if the contents of access rights byte allow, only then can the requesting program access the program segment corresponding to the descriptor. The base and limit fields of the descriptor, base and limit field of the descriptor contain information. These are base and limit contains the information which is used for finding out the physical address of the program segment corresponding to the descriptor at which the program segment is placed for the execution of the program. Okay, the upper position, which is called intel, has been reserved for future purpose for the compatibility with the future processor, and the middle position. So these are actually, so it is 8 bytes long descriptor. So 0, 1, 2, 3, 4, 5, 6, 7. So 0 to 7, these are bytes, and this is 16-bit wide, 0 to 15. So 16-bit information is stored here in this position, and in this middle position, A, type, S, DPL, and P. Actually, these are called access rights byte, access rights bytes. So this bytes has certain significance, like A. A denotes the accessed, means whether the segment has been accessed or not. Okay. If A equals to 0, that means segment has not been accessed. And if A equals to 1, then segment selector has been loaded into segment register or used by selector test instructions. Okay. The next is the type. So type, it actually combinations of 3 bits. Okay, 3 bits, and these bits are called as per selection of data segment or code segment. Okay, data segment or code segment, and this S actually defines whether code or data segment descriptor or system segment descriptor. Now, if any if this type is your for code segment, then what will be the bits? This lower bit is, suppose it is divided into 3 bits in this way: 0, 1, 2. So 0 bit is called the executable bit, that defines the type of the code segment, which is equals to 1 or equals to 0, and then the conforming bit, which is code segment may only be executed when different uh, descriptor table has been accessed or not. And third is the readable or writable. Okay, means data segment may not be used for written purpose, or code segment may not be reading purpose. Okay, so if it is code segment equals to 1, then that is to be used for read purpose. If this bit is 0, then it is for writing purpose. Okay, for writable purpose. Is it clear? The next bit is called the segment descriptor. So whether it is a code segment or data segment, or it is a system segment descriptor or get descriptor. So it is defined by this S bit. If it is 1, then code or data segment descriptor is used. If S is 0, then system segment descriptor or get descriptor is used. The next bit is DPL, which is called the descriptor privilege level, which is in this case the segment privilege attribute used in privilege test. And the next is the P for present, which is P equals to 0, means no mapping to physical memory exists, base or limit are not used, and P equals to 1 means segment is mapped into the physical memory. Okay, so that is the type of data segment descriptor or code segment descriptor. So here it is given, all the bits has been given in this way. Okay, so what I have told you right now, that has been given individually, the bits configuration, access right bytes. So that's all for today, and that's all for 80286 microprocessor. So on next week I will discuss about the 80486 microprocessor. Okay, so I will give you the I will give you the notes of this 80286 microprocessor, which will be uploaded in Google Classroom. You must go through it. Okay. Thank you all. Thank you. So I will end my meeting.